All right, so a lot of you guys actually already went through these chapters in the book, so good for you. This will probably be a little bit of a review. This PowerPoint is pretty much a very easy one. We're easing into a lot of the ultrasound physics. We're going to talk about some specific ultrasound topics in terms of basics towards the end of this PowerPoint, but we're going to start off with some of what we call like a math review or a basics review. So a lot of this is going to be a little redundant for you guys, but just to make sure that we get all this information kind of fresh in our minds. So we are going through chapters 1, 2, and 3. The main things that are going to be different with these chapters are what we call our parameters. So we'll get to those in a second. That's like the foundation of all of ultrasound physics. Everything goes back to those parameters. They're like the foundation or the building blocks of how we create our image. So let's start with our math basics. Oh my God, how did I should have double checked that my PowerPoint was going to come over appropriately. Can anyone even read that on the screen? It's just
It's not
me.
that bad.
All right, I gotta get like my glare figured out over here. Okay, hold on 1 second, guys. I should have looked at this before I uploaded it. All right, so let's start off with some definitions to begin with. A lot of this kind of goes back again to that simple math, but we need to know how to compare two different things in terms of physics for ultrasound. So we're going to be using these definitions quite a bit, particularly directly related and inversely related. So those are really big in terms of getting into those parameters. So if you have two items that are unrelated, that means they have no relationship to each other. When one changes, the other one is not affected by that change at all. There's no communication between those two. When you have something that is related, or what we call proportional, that means that there's some type of affiliation, but it's unspecific. So we need a little bit more information about that relationship. Now we can further kind of define what that relation is, or that proportionality is between those two items when we talk about directly related or inversely related. So if you have two items that are directly related, that means when one changes, the same exact change is going to happen to that other item. So if you, I think your textbook gives a lot of examples. When you work out at the gym quite a bit, you are increasing your working out, so you are increasing your muscle mass, right? Now, on the flip side of that, if you have something that's inversely related and you are increasing how much you're working out, you are decreasing your overall BMI, right? So you can have these two items that have specific relationship or affiliation with each other, but we need to know what happens when something happens to one item, what is happening to that other item that it's related to. So we are constantly talking about directly and inversely related relationships. We also can have a reciprocal relationship, and this is kind of like another form of an inverse relationship, and it's when we have two items that if you multiply them together they equal 1. So this is kind of where we get a little bit into our fractions and we have to do a little bit more math. So our graphs are also super important with ultrasound. This is something that we should all be aware of. Graphs typically have an x-axis on the horizontal line, and our y-axis is going to run vertically of our graph. In ultrasound, our x-axis is typically always going to be time, and our y-axis is usually going to be some type of what we call a bigness parameter. So the overall power or intensity of our ultrasound wave. So x-axis is usually time, y-axis is usually going to be a bigness parameter. And again, here we're looking at how to graph something that has some type of relationship, right? So if we look at our green line on the graph on the left side, what type of relationship would we say those two items have that we're graphing?
Direct.
Good, right? So as time is increasing, so is that overall power. So that same exact change is happening to both items. What about the graph on the right side?
Inverse.
Good, yep. inverse relationship or an indirect relationship. I kind of go back and forth between saying inverse or indirect. If that confuses you guys a little bit, just keep in mind that those mean the same thing. Next, we have units. This brings me back to when I was in high school. My dad is a scientist, and I always kind of struggled with math a little bit growing up, and he would help me do my math and chemistry homework. And I would just remember him sitting at the kitchen table going, units, units, units. So when you guys are taking your registry, just picture like a grumpy old man yelling units at you. So hopefully you never forget to put a unit on your numeric value. So we always have to have some type of unit when we are talking about ultrasound physics. There are some exceptions to that. There are some unitless values. We don't talk about them too much, and they're kind of just there to confuse you. But you should know in your mind that every numeric value needs to have an appropriate unit associated with it. The reason is that units provide us certainty and quantification. So that's how we can measure something. That's how we can create these precise images, because we have that certain specific amount of whatever value we're looking at. So length is going to be required for any type of distance or circumference. An area unit is going to be anytime where we have a unit squared, and a volume is going to be when we have a unit cubed. We also need to understand the conversions between that. I think in lab last week, Chelsea had mentioned when you are getting measurements of certain pathologies, the machines are going to give that to you in centimeters, and you need to convert that to millimeters. So that's just a very small, simple type of conversion. We need to be able to take that a step further in terms of the physics component to it. So we also need to know the powers of 10, and this kind of goes with that converting millimeters to centimeters and vice versa. This is something that you may have remembered from your math classes, but I particularly didn't really remember getting this prior to ultrasound physics when I was a student. And it's basically when you have these circumstances of numbers that are either really, really large or really, really small. So say you have this tiny, tiny value and it comes in as 0.000009. Are we really going to take up the time and the space to write out all of those zeros? No. Let's make our life a little bit easier, and let's kind of use what we call this scientific shorthand. This is where we give values exponents. So if they're really large and we don't want to have to write out all of those numbers, or they're really small and we don't want to have to write out all of those numbers, we're going to give it an exponent to kind of get rid of some of that. So there are certain rules that go with the powers of 10. When you have a positive exponent, that means that your number is really, really big. It's going to be a value greater than 10. So any number bigger than 10 can have a positive exponent. Now, when you have a negative exponent, this means that your number is very small, so it's 0.000 something. Any number that is smaller than 1. Now, when you have a 0 exponent, that means that your value is somewhere between 1 and 10. So we're not giving exponents to the number 9 or the number 6. We're really not even giving exponents to anything kind of smaller than 50, I would say. So we're not really doing that for anything in the hundredths place. We're really doing it for numbers in the 100,000s and so on and so on and so forth, and in terms of decimals with those really small numbers. So how do we calculate this? How do we know what value exponent to give a really large or a really small number? We're going to be moving the decimal space to be in the position between the 1 and 10 value. So if you are moving your decimal to the left, this means you have a very, very large number that you're trying to make smaller. You're moving your decimal to the left. That's going to give you a positive exponent, however many moves you had to make. Same thing if you are moving your number to the right. So this means you have a very small number. You have 0.000 something. You move that decimal to the right until you get into a space between the 1 and 10 value. That's going to be a negative exponent for that. It's really important that you know the reason why you have a positive exponent versus why you have a negative exponent, because you could make a number extremely big if you are incorrectly putting a positive exponent, or you could make a number extremely small if you are putting an incorrect negative exponent. So we have a few examples here. What would that first number be if we were to put that into scientific shorthand?
Would it be 5.78 times 10 to the 5th?
Good. Yep. And what about that second number there?
Would it be 2.6 times 10 to the negative 4?
Good. Awesome. All right. You guys are great with that. So on the regular PowerPoint, this chart does not look particularly like this. You can see kind of the difference between a really, really large number and a really small number, and the different prefixes and symbols that we give to those values. We use a lot of the symbols. So this is something that you have to familiarize yourself with. We are constantly using centimeters, right? In ultrasound, we're using millimeters. We even are using a lot of micrometers in terms of ultrasound. So familiarize yourself with the symbol, what it means, and how much that actually equates to. Another way you can kind of look at that, if you are a visual learner, this chart's probably not going to come over, but there is another slide in the PowerPoint that shows you how those numbers, as they get decreasingly smaller by one value place, what that looks like, what that prefix is, and what that symbol would be for that particular unit. All right, so let's get into those parameters. We are mainly focusing on sound waves for the rest of this PowerPoint. Now, this is talking about sound waves in general. This is not talking about how sound waves behave in ultrasound. So sound waves in ultrasound, we are factoring in soft tissue, things like that. So today we're mainly just talking about how sound waves behave in general, and we're going to kind of touch upon what happens to them as they travel through certain types of media. So in your ultrasound textbook, your Edelman book, he has a quote right at the beginning that says, in diagnostic ultrasound, sound pulses created by a transducer travel through tissue or media. Reflections arise from the boundaries between the structures in the body, and they return to the transducer to be processed into images. So on a very basic level with ultrasound, we send a sound wave in, it reaches an object or what we call a boundary, it reflects off it back to the transducer, and the transducer is going to process that reflected wave. So there are a lot of variables that occur between this process, right? There are a lot of things that can happen to that sound wave as it's traveling in. There are a lot of things that can happen at that boundary reflection. And then there's a lot of things that can change that wave on its way back to the transducer. So it's a very delicate, complicated relationship between the ultrasound system, the transducer, the original sound wave, the reflection in the body, and then the sound wave being sent back to the transducer. So we are going to learn, the premise of this course is to learn all about what happens in that relationship. So our sound waves, right? Energy is going to be carried by wave, all types of energy. So this is sound, heat, light, magnetic. You cannot have energy be carried in a stagnant environment. So everything has to be transmitted in some type of a wave. Now with sound waves, they are what we call mechanical waves. And this means that a mechanical wave has to travel by some type of vibration. We'll talk about that a little bit more. It also requires a medium to travel through, and it cannot travel in a vacuum. So when you think about space, right, there's no air, there's nothing, right? It's just a vast type of environment. It's technically considered a vacuum. So when you don't have a medium for that sound to travel through, it's not going to travel through space. And that's why we can't hear anything in space. Everything is silent because there's nothing for it to go through. Sound also is always going to travel in a straight forward line. Sound never travels backwards. So if you're standing behind your friend and you're both facing forward in the same direction, and your friend is talking, but you're standing behind them, you're not going to hear what they're saying, right? Because sound just doesn't turn around and go backwards. It's only going to travel in a forward fashion. Now, sound is also what we call a longitudinal wave, and this concept is a little bit confusing, and I do have a little segment in your module about longitudinal waves. It talks a lot more about compression and rarefraction, and that is what happens to the particles as a sound wave travels through it. So we just said that sound needs a medium to travel through, and as it travels through that medium, it actually kind of changes its composition. It has an effect on those particles. So those particles, as it's traveling through, they're going to squeeze together at some point, and then they're going to pull apart at other points. And when that happens, that constant squeezing and stretching and squeezing and stretching, it's going to cause these vibrations. And those vibrations are how that sound wave is going to travel through. Now, when we are describing and we're learning about sound waves, we're graphing them in what looks like a transverse wave, but in reality, we are just graphing the areas of that squeezing together and that stretching apart, the compressions and the rarefractions. So the YouTube video that I posted in your module, she has a really great way of explaining that and explaining how we graph those particular points. So don't get confused by what is in your textbook. It's a very vague section in your textbook. Use that section that I put in the module to help you get a better understanding of that. If we also look at this picture here on the right side, we can kind of see some of these examples showing that compression and rarefraction a little bit better. So let's look at the top right sound wave. These are all different ways that you can graph sound waves. So this top right picture, you can see the areas of compression here and the areas of rarefraction here, right? Compression, rarefraction. We're graphing those peaks and those valleys of what's happening to those particles as those sound waves are traveling through it. So the sound wave itself, it's actually kind of traveling in this forward, backward, forward, backward, forward, backward, but it's still going in this forward direction. Does that make sense? So it's like, it's almost like I think I put a picture of a slinky in there too, right? So you throw a slinky in one direction and it kind of vibrates back and forth as it goes in that longitudinal straight line. So next we're going to get into our variables. Again, I don't really know why this PowerPoint is coming over such an odd way, but how can we tell that a particular wave is in fact a sound wave? We just said that all types of energy need to travel by waves. So how do we know that we're actually dealing with a sound wave? They have to have 3 acoustic variables. Now, acoustic is always going to reference sound. They have to have pressure, density, and distance. This is how a sound wave is going to be categorized as an actual sound wave and how it moves and behaves. So you have to have pressure, right? That sound has to kind of apply a particular amount of force in an area. It also has to have mass to it. So it has to have some type of weight to it as it's traveling through. It has to have a distance. That means it has to be moving, right? And that's where that oscillation comes in. Typically that movement or that motion while that sound wave is traveling a distance is going to be the variable that oscillates. Our density isn't really going to change. Our pressure sometimes can change, but usually our distance is going to be the path where that sound wave can oscillate, right? Because we have the space for it to vibrate back and forth. Next, we have our actual parameters. So we know it's a sound wave. We know how a sound wave can behave and what it needs. How do we describe a sound wave? Because not all sound waves are the same, right? Think about like if you've ever been to the air show, what those sounds sound like versus when you're listening to calming music. We know that there are all different types of sound. So we describe those waves by using these 7 parameters. Now we have period, frequency, amplitude, power, intensity, wavelength, and propagation speed. Now we're going to go into each of these parameters on the next few slides, and there are a few kind of terms that are going to be consistent between the slides. So you have to know that when we're talking about the source of the sound wave, we are talking about the ultrasound machine and the transducer. Where is our sound wave coming from? What is that source? It's being manufactured by the ultrasound system. Also, the medium, we are now talking about human tissue. So if it says it needs a medium to travel through, we are talking about human tissue. All right, period is going to be our first one. I'm going to pull up on the side my PowerPoint just so I can't read it like this. Just give me 1 second. I'll make sure my next PowerPoints come over a little bit easier for our lectures. Okay, so period. This is kind of exactly what it sounds like when you think of a time period. You think about a little blip in time, like the, whatever era you're talking about. And that's kind of the same concept when it comes to period for a sound wave. We're talking about how long does it take for one wave to complete one cycle. So we are looking at something being measured in a value of time. So we need to make sure that our units match up with that. The typical value range in ultrasound is going to be 0.06 to 0.5 microseconds. Okay, going back to those units here that we just talked about. So this is something that is happening very, very quickly, especially when we are talking about sound waves in ultrasound. Think of how fast that is to complete a cycle for a sound wave. That's extremely, extremely fast. So how is this going to be controlled? Is this something that we can adjust as the sonographer? Can we manipulate this in terms of changing the sound wave? We cannot. So this is only going to be controlled by our sound source only. Our ultrasound machine determines the amount of time it takes for a wave to complete one cycle. We can't select this. Now, the only thing we can select and we can adjust is what type of transducer we're using, right? So as we know, our curved transducer, that's going to have a lower frequency, which we'll talk about the relationship with frequency in a second, but that is going to be traveling at a slower rate. So that period is going to be longer, right? That's the only thing that we can adjust for. Within that transducer, we get a certain range, and that's pretty much all we have to work with. So here we have a very basic graph of a sound wave. Now, a cycle is going to be one peak and one valley. So that is going to be one wave, or valley to valley, well, peak to peak, or valley to valley. That is going to be one wave cycle. So how much time did that take to occur? Now, in a perfect world, on an exam or on your registry, your x-axis is going to have the units of time on it. So you would be able to actually calculate what was that period just by looking at the peaks and the valleys of that waveform. Next, we have our frequency. So we already know a little bit about frequency, right, from our intro course and from actually scanning. So what is it? It's the number of cycles, of wave cycles, that occur within 1 second. So period was how long did it take to complete one cycle. Frequency is now saying, hey, I'm giving you 1 second. How many cycles can get by in that 1 second? So similar in terms of time, right? We're looking at something to see its time, but frequency is saying, I'm giving you that time. I'm saying, hey, in 1 second, what can you do? Now, that is also going to be something that we talk quite a bit about in terms of relationships to other parameters. So the units of frequency are going to be units per second, or what we commonly call as hertz. So hertz is going to be the units per second. Typically, one cycle is going to, 1 cycle per second equals 1 hertz. So this is where we get our value range of 2 megahertz to 15 megahertz, right? So again, go back to those units. What does mega mean? What does that numeric value actually look like? How big is that number? So that is saying to us, when we have this really big frequency number, that's saying, hey, we can get a ton of cycles to occur in 1 second when we have these really large hertz values. What is this going to be controlled by? This is only set by our machine and our transducer selection as we know that. Now, you're probably thinking, well, wait a minute, you made me like drop my frequency while I was scanning to see something a little bit better for penetration. You have a set range for each transducer. We'll learn about our transducers as the semester goes on, but as you know, when you are selecting your transducer, you are selecting a probe that falls within a frequency range. So you can adjust it within the range of the transducer. You can't set it to whatever you want it to be if it doesn't fall within that range of the transducer. And then just a little reminder, we should probably all have remembered this, but when we are talking about regular sound waves, that is coming in at kind of a value of 20 to 20,000 hertz. So that is anything that we can hear, right? Anything less than that is going to be infrasound, and anything greater than that. So anytime we have more sound cycles that are occurring per second, we have a higher frequency. We cannot hear that when it's greater than 20,000 hertz or 20 kilohertz. So a little different than megahertz on our previous slide. This is talking about what can we hear, and then what frequency becomes too high that it's no longer eligible for us to hear. If you guys have ever done like those YouTube videos or those like challenges where you test your hearing, and as the frequency gets higher and higher, it becomes softer and softer, and at a certain point you can't hear that sound anymore. And it actually gets, the frequency that you can hear at gets lower and lower as you get older. So if you have a really young sibling, they're going to be able to hear something in that higher audible range than somebody, you know, maybe your parents could. So it's very interesting to see, but just remember, anything greater than 20,000 hertz is going to be considered ultrasound. So here we can kind of see the difference of what these waves would look like in terms of their frequency. Now, when you have a low frequency, we can see we have kind of like a very relaxed type of wave here, right? And then we have a medium frequency, so we're picking up our number of cycles that are occurring per second. And then we have this guy down here, really high frequency, right? So you almost have double the frequency in the high frequency than you do the low frequency. So think about a wave at the ocean, right? Actually, I want to wait till we get to wavelength to use that analogy. But you can kind of see if this period of time right here, that was the worst line I've ever drawn. Hold on, let me do another one. So if we were looking at this in terms of an XY graph, and this was 1 second in time, what would our frequency be for the low frequency?
Two?
Mm-hmm. Yep. And what about the high frequency? I'm sorry, the low frequency is going to be 1.5. I'm sorry, if it were 2, it would have been right here. So if this is 1.5 cycles that are occurring in 1 second, what about the high frequency one?
3.5.
Good, 3.5. Yep. All right, so now we're moving into those bigness parameters. So when I talked about the graph and how we usually have time on our x-axis and we usually have some type of bigness parameter on the y-axis, we're talking about, to put it very vaguely, the overall strength of that sound wave. Now there are certain parameters that are associated with that, and that's going to be our bigness parameters. Those are amplitude, power, and intensity. So really, how strong is that overall wave? How much of an impact is that sound wave having on the particles as it's traveling through, right? Where are we graphing those compressions and those rarefactions? So we'll talk about each one individually, but they are so closely related. Our first one, amplitude. We use amplitude a little bit more than we do power and intensity. And what actually is it? So it's the scale size of the wave, right? How big is this wave? And it's showing the difference between the maximum and the minimum values and then the average. So the average is always going to be our x-axis. And then from there, if we're looking and graphing amplitude, we are going to see how far away does that wave get in terms of how strong it is, right? Its maximum value, and then the minimum value with it as well. So we're looking at amplitude in any type of unit that has an acoustic variable. So any of those pressure, density, or distance units, that is going to be the unit that we use for amplitude depending on what information we are given. We typically are also using decibels for amplitude. So we can use any unit of acoustic variable, but we're usually going to be given the decibels in terms of how to calculate or graph something in terms of amplitude. The typical value range is going to be 1 million pascals to 3 million pascals. It is going to be controlled by the ultrasound machine only, and naturally the strength of that wave is going to decrease as it travels through a medium, right, depending on that medium. We can adjust it initially, but it's not something that we commonly adjust. So it is one of those kind of in-depth user operator controls that there is the capability to adjust it before you start scanning, but that's not something we are typically doing in our day-to-day job. So it's mainly controlled by the ultrasound source when we're selecting our exams and our transducers. And as we know, the strength of a sound wave is just naturally going to decrease as it's traveling.
Is
So
amplitude,
here we, yes.
Is amplitude like different from gain?
Yes, so we're going to learn about gain towards the end of this semester, and what that does to our reflections that we receive back from the transducer. So gain is something that happens after we've received it from the transducer. So this is, we are sending sound waves into the body. What are the characteristics of those original sound waves? Gain is something that's a little bit after the fact, but we will get there as we move forward. So here we have our graph on the left side. This x-axis is always going to be our average when we're looking at amplitude on our y-axis. Okay, so that's always going to be our baseline. Now, when we're looking at the strength of that sound wave as it's traveling through, we're saying that this is the maximum value for our amplitude right here. So that's going to be the value that we are looking at, that we're trying to get a unit for. And then same thing down here. So that is technically what we would call the minimum, but it's the same strength, because remember that wave is oscillating as it's traveling through, right? It's vibrating back and forth as it's traveling through. So it's going to be, right, like if here is 0 and then we say we have 5 pascals, 10 pascals, or decibels, then we would have -5, -10. There's still a minimum value, right, because it's a negative number, but it's still showing the overall strength of that sound wave. So our amplitude is going from the average, which is our x-axis, our baseline, to the peak or the valley. Now look at the examples on the right side. I don't know if you guys can tell the difference between those wave colors, but which, that already says it on the side there, but look at that blue wave, right? Here's our baseline, here's our average, here's our 0. How much stronger is that blue wave than the red wave? Right? The blue wave, the amplitude is coming in at 100. The red wave's amplitude is coming in at 20. So which wave do we think is going to be stronger in terms of power?
The blue wave.
Good. Good. Hopefully that was an easy one. Seemed a little bit hesitant. Everyone seemed a little hesitant to answer that one. But think about how you would want your sound wave to be if you're looking at a really big patient, right? If you want to get your sound wave all the way into the body, you know the strength of your wave is going to decrease as it travels. Do we want to originally start with the red wave? Probably not, right? We would want to start with the wave that has the strongest amount of power initially, within reason. Next, we have actual power. So this is very similar to amplitude, and we can kind of very easily get confused between power, intensity, and amplitude, but power is going to be proportional to amplitude by amplitude being squared. So it's going to be a larger value than amplitude. So power and amplitude are always going to be directly related, right? When the magnitude of that wave increases, that means that the power of that wave also increased, right? That means it's a stronger wave. So power technically in the textbook world is going to be the rate at which power is performed. So if you think about basic electricity values, right? That's all power. That all goes by watts. So that's going to be the same thing for an ultrasound wave. Our typical value range for power is going to be 4 to 90 milliwatts. That it's going to be controlled by the sound source only, and very similar to amplitude, it's going to obviously decrease as it travels through tissue. Again, we can adjust this initially, but it's not something that we are doing. So when we have our imaging presets and we select a transducer and then we select the exam that we want to use, a biomechanic or a bioengineer has already decided which types of initial parameters are going to be appropriate for those types of exams. So when you're selecting your exam preset, you're already deciding and adjusting what kind of power and what kind of amplitude you want, because someone else has already done the experiment on it. Someone else has already said, hey, typically when people are doing clinical abdominal ultrasounds, this is the appropriate power to start at. So that's already being done for you in the background. It's not something that we are going to go in and adjust ourselves, but it is something that you can get into the details of the machine on and look at a little bit further. Next, we have intensity. So again, also going to be very closely related to power and of course amplitude. Similar to power, it's going to be proportional to amplitude by amplitude square. It's going to be directly proportional to power, and we have our intensity equation there at the top. When we are calculating for intensity, we are taking our power and we are dividing it by the area. So we are saying, how intense is this sound wave as it's traveling through a specific area of this tissue? So now we're taking it a step further. We know how big our sound wave is. We know how strong our sound wave is, but now I want to say, okay, as it reaches this portion of tissue, how intense is it on that tissue in this area? So that's why we're factoring in that area into this equation. So it's the concentration of energy in a sound beam. We're going to learn all about sound beams in a few weeks, so it's going to go a little bit further. Intensity might make a little bit more sense at that point. And again, similar to amplitude and power, the other bigness parameters going to be controlled by the ultrasound system itself. Decrease as it propagates through the tissue, and we can adjust it, but we are not commonly adjusting it. So put a little asterisk next to your intensity equation. Really, all equations in this course are going to be free game for the registry. So next we have wavelength, and this is kind of going back to the relationship with period and frequency. We talked about period, we talked about frequency, we talked about our bigness parameters. Those were all kind of talking about how strong a sound wave is and how fast a sound wave is. Wavelength is saying, how long is this sound wave? How long does it take to complete one cycle? So we are looking at distance with this. Wavelength and frequency are going to be inversely related. So this means that as frequency increases, right, the number of cycles that are occurring in 1 second, as that gets higher and higher, that means our wavelength is getting shorter and shorter. So that's going to be decreasing. So when we're looking at our chart here, our units obviously going to be anything in distance or length. Our typical value for ultrasound is going to be 0.1 to 0.8 millimeters. per wave is going to be controlled by both the ultrasound system and the medium. So this all depends on the patient that you're scanning and the organ that you're scanning. This is going to be the only acoustic parameter that is determined by both, and it is not adjustable, right? Because we can't really control that from the sound source, and we can't really control what type of medium it's going to be traveling through. So let's look at our little diagram here. Looks very similar to the rest of them, right? So you can really get a lot of information from one graph of a sound wave. It all depends on what units they're giving you in order to determine what they're looking for. So you use that as kind of like a little trick that they're trying to use. Look at your x-axis. Is it giving you distance? Is it giving you time? Look at your y-axis. Is it giving you decibels, right? That's going to say, okay, what value am I looking at? What parameter am I looking at? So your wavelength is the distance it takes to complete one cycle. So peak to peak or valley to valley. What is that distance? Now, going back to frequency, we just said wavelength and frequency are inversely related. So as frequency increases, your wavelength is going to decrease. If you think about when you're at the beach and it's a very calm beach day, right? There's not a lot of waves. Think about how low those waves are, right? They're low, they crash onto the beach every few seconds, right? So they have a longer wavelength and a lower frequency. They have an increased wavelength and a decreased frequency. Now think about when a storm is coming and you're at the beach and the waves are just like crashing constantly on the beach. They're a little bit higher. They're coming in a lot faster, right? So now you have an increased frequency and those waves are really, really short because they're crashing, 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 crashing. So think of that beach reference when you're trying to think of what is happening in terms of my wavelength and what is happening in terms of my frequency. If I have a really high frequency, would it make sense that I have a really short wavelength? No. You're going to have, well, excuse me, yes. Forget I just said that. If you have a really high frequency, you have to have a short wavelength because there's no way that in a period of time to complete that 1 second, you can't have a bunch of long waves and still expect to complete a ton of cycles in a 1 second period of time. So that is why the two of them are going to be inversely related to each other. Everything kind of goes off of that wavelength and frequency relationship. So we are constantly coming back to that. So here, this is kind of another little visual. Again, think of that beach, right? Think of the weather. This is going to be high frequency is going to be right before a storm comes in, where we have those constant crashing. They're occurring every few seconds, whereas you have that calm beach day, that low frequency with the long wavelength. So this, you have a decreased frequency and an increased wavelength. High frequency, you're going to have an increased frequency, a decreased wavelength. Next, we have our wave phases. So this is what we have when we have two sound waves that are occurring at the same time. They're traveling from our system at the same time. Now, in clinical ultrasound, we are creating these really high quality, precise images. Do you think we're just sending in one sound wave at a time? No, that would take forever to get an image. Our image would really not be useful. So our transducers are sending in multiple sound waves, usually at a time. Sometimes they go in a particular pattern. We'll get to all of that. But we are usually looking at at least two waves that are occurring at the same time. Now, when these waves are what we call in phase, this means that their maximum values are occurring at the same exact time and location. So when we'll talk about that in a second, I'm getting a step ahead of myself here. When we have two waves that are occurring out of phase, that means that their maximum values, so their peak values, are not occurring at the same time in the same location. So the diagram here, pretty self-explanatory. The picture on the left side, the purple wave and the blue wave, although their maximum values are not the same, right? Their amplitudes are not the same. They are still occurring at the same exact time in the same exact location. Now, if you look at the out of phase waves, that purple wave, that peak value is occurring just slightly before that blue wave's peak value is occurring. So that's going to be considered out of phase. Now, when we have these two waves that are either occurring, the max values are occurring at the same time, or they are not occurring at the same time, we consider that wave interference. So what is happening to those two waves? How are they behaving? What happens with each in phase or out of phase wave? So when you have an in phase wave, they are going to join to form at that same exact time. Actually, both do. In phase waves and out of phase waves are going to join to form at the same time. And this is what we technically consider as wave interference. When you have two in phase waves, right, so their maximum amplitudes, their maximum values are occurring at the same time, they're going to join to form one wave that has a greater amplitude. So it's like you're adding the amplitude from the smaller wave to the larger wave, and now you're getting one even bigger wave, right? And that's going to be considered constructive interference. Now, when you have those out of phase waves, they're still going to join to form one wave, but it's going to have a smaller amplitude. So now you're subtracting that amplitude, the amplitude of the smaller wave from the larger wave, and you're getting an overall one single smaller wave. That's going to be considered destructive interference. Now, when you have two out of phase waves with equal amplitudes, this means you're getting zero, right? You've got zero amplitude now, because if you have one wave that has 50 of an amplitude and you have the other wave that has 50 of an amplitude, even though the 50s are not occurring at the same time, when you subtract the equal amplitude from the other wave, you're getting zero. So you're completely losing that wave, and it's going to be complete destruction of that wave. So that's no longer interference, that is total, complete destruction. Next, we are moving into our propagation speed. So one of our last parameters that we are going to talk about. Propagation speed is the rate that the sound wave is going to travel through a particular medium. So this is something that is only going to be controlled by that medium itself. We can't adjust this. We can't say, okay, I want the sound wave to travel at this speed throughout this tissue. We don't get to determine that. Sound only determines that depending on what tissue it's trying to get through. The average value of that sound wave traveling through human tissue is going to be between 500 and 400 meters per second. Again, that's all going to depend on the tissue. We have skin, we have fat, we have muscle, we have organ tissue, we have bone. So that is even going to vary even further. And we do have a slide about some typical values for the propagation speed per tissue. Now, this is going to be in units of meters per second. In our world, we're typically looking at millimeters per microsecond, and it's going to be any distance divided by time. That's how we can calculate that type of unit. Also need to be aware that your speed is going to equal your frequency times your wavelength. It's really important for you to be aware of your units when you're using these calculations, because speed, this equation is giving you speed in meters per second. So you would need to break that down even further to get millimeters per microsecond if that's what the question is asking you to do, or that's what the scenario is giving you. So here we have how those values are going to vary depending on the human tissue that we are looking at. So we can see our diagram on the right side. Air is going to be, we already know air is not our friend, right? When you guys have bowel gas, we can't see through anything. We can't see through your lung tissue. When you don't put jelly on the transducer and it's exposed just to the air in the environment, we're not seeing anything on our screen. So it's going to travel really, really slowly through air, therefore not falling in the range of computing an image. Water is going to be a little bit closer to human tissue. It's actually going to be pretty close to human tissue. So when you put jelly on that transducer, it's water-based jelly, right? Now we're getting our screen popping up. When you are looking and scanning through your gallbladder, that's the type of fluid, right? That's showing up nice and beautifully, our bladder. So that's going to be more of a speed that is equivalent to our human tissues. Now, when we're trying to look through metal, this is kind of the opposite problem of what we have with air. Now it's traveling way too fast. So now it's beyond the normal value and range to compute an actual image, because the sound wave is going to hit that metal and it's going to make those vibrations go crazy, right? So air is kind of like a what we call a quote unquote vacuum, right? There's no medium in the air, so it has nothing to travel through. So therefore that sound wave is not going to really do anything. Metal, it's the opposite of that. It's bouncing off of that medium too often, too fast. So that propagation speed is going to be way too fast for us to get an actual picture of. You will see sometimes people will have metal implants in their body, and you're going to get that extreme dropout on your image. Now, if we look at our diagram on the left side, this is a little bit more appropriate. We are typically going to be averaging, the average medium that we're looking at in ultrasound is going to be soft tissue. So that is going to come in at about 1,540 meters per second. That means that that sound wave is traveling 1 mile per second. Think of how fast that is, right? That's a ridiculous speed. Now think of what that frequency is going to look like. What are those waves going to be looking like, right? That wavelength is going to be so short, that frequency is going to be so high, and the speed is so high. Now, as our tissue gets a little bit denser, that sound wave is going to travel faster and faster. So our bone, if we look at it, 3,500 meters per second, that's really fast. So again, we're falling into that range of the sound wave not being able to compute an actual image because it's traveling too fast and it's just vibrating too much for our system to consider that a normal clinical range. Next, we have our medium characteristics and speed. So we just said propagation speed is going to be the only parameter that is determined by the medium only. So only the medium is going to affect the sound wave in terms of its speed. Now we also have stiffness and density. These are the main characteristics of the medium that we are looking at. So stiffness is going to be the ability to resist compression, right? As we know how stiff something is. Can you squeeze it? Is it soft and squishy, or is it really hard and you can't compress it? The stiffer the material, the more it's going to retain its shape. Again, that kind of makes sense if you're trying to squeeze something, right? If you have a ball of pizza dough, that's not stiff at all, right? It compresses super easily. When you squeeze it, it does not retain its shape. So if you have a bowling ball, it resists any compression if you try to squeeze it, and it's going to keep its shape. So stiffness and speed are going to be directly related. So that the stiffer something is, think of that metal, think of those bones, they're really, really hard. They're going to resist that compression. The speed is going to travel through them extremely fast. So if you have an increase in stiffness, you have an increase in propagation speed. This is going to also be the medium characteristic that has the greater effect on speed. Density is going to, of course, have an effect on the propagation speed, but it's going to be more affected by the stiffness of the medium. Now, medium density, what is that overall relative weight of this medium? If the volumes are the same, the denser medium will weigh more. So if you have two mediums, the one that weighs a little bit more is going to have the greater density. Now, density and speed are going to be inversely related. So as your density gets heavier, your speed is going to decrease. If your two mediums are equally stiff, right? So they don't compress, they retain its shape, but the denser medium, you have one that weighs more, that one is going to have a slower speed. So you basically, if you want to have the faster propagation speed, you want to have the stiffest material with the lightest weight, the lightest density in order for it to travel through. So a little rule of thumb, oh, this came over great. The rule of thumbs is what your textbook is going to tell you to do to remember the effect of stiffness and density on speed. Basically, speed is, as we know, is going to be determined by the density and stiffness of a particular medium. If you have your stiffness and your speed and both of your thumbs are upward, right, because they are directly related. Stiffness increases, speed increases, they are the S same. So all of your S's are going to have the same effect. Now, if your stiffness decreases and your thumb is down, and your speed decreases and that thumb is down, they're still doing the same thing, right? Because they are directly related. The same change is happening to them. When it comes to density, they are inversely related. So if your density increases, your thumb is up, your speed decreases, thumb is down. So you can remember S for same, D for different, or decrease for density. So not a ton of like super complicated information in this PowerPoint. Your textbook does have a lot of good images that you guys can go and reference. They also have a ton of very helpful practice questions at the end of each chapter, so make sure that you do those. We are going to obviously continue to build upon sound as each week goes by. You don't necessarily have to review the chapters before we have class, but if you find that that's helpful for you, absolutely go for it. You can bring questions at that time too. If you guys feel super confident on something, you can kind of just say, yeah, we didn't really need the review on the graph, right? Because we already kind of reviewed that in our textbook. So just keep me updated on how it all goes. Your quiz for this week will be due on Sunday night at midnight, just like your abdominal and small parts quiz as well. But if you have any questions in the meantime, please feel free to reach out to me. I'm going to stop the recording.